OK, I didn't talk about parent. We can do that a little bit. So parent, we're initializing to say parent of S is nobody. And then whenever we visit a new vertex v, we set its parent to be the vertex that we came from. So we had this vertex v. We had an edge 2v from some vertex u. We set the parent of v to be u. So let me add in what that becomes. I'll change colors yet again, although it gets hard to see any color but red. Let's see. So we have S. When we visited A, then the parent of A would become S. When we visited Z, the parent of Z would be A. Parent of X is going to be S. Parent of D is going to be X. Parent of C is going to be X. Parent of F, it could have been either way, but the way I did it, D went first. And so that became its parent. And I think VC was its parent. OK, so that's what the parent pointers will look like. They always follow edges. They actually follow edges backwards. If this was a directed graph, graph might be directed that way. But the parent pointers go back along the edges. So it's a way to return. It's a way to return to S. If you follow these pointers, all roads lead to S. OK? Because we started at S, that's the property we have. In fact, these pointers always form a tree. And the root of the tree is S. In fact, these pointers form what are called shortest paths. Let me write down a little bit about this. Shortest path properties. If you take a node and you take its parent, and you take the parent of the parent, and so on, eventually you get to S. And if you read it backwards, that will actually be a path in the graph. And it will be a shortest path in the graph from S to V. Meaning, if you look at all paths in the graph that go from S to V, so say we're going from S to V, how about that? We compute this path out of BFS, which is follow parent of V is C, parent of C is X, parent of X is S. Read it backwards. That gives us a path from S to V. The claim is that is the shortest way to get from S to V. Might not be the only one. Like if you're going from S to F, there's two short paths. There's this one of length 3. There's this one of length 3. It uses 3 edges. Same length. And in the parent pointers, we can only afford to encode one of those paths, because in general, there might be exponentially many ways to get from one node to another. We find a shortest path, not necessarily the only one. And the length of that path, so shortest here means that you use the fewest edges. And the length will be level of V. That's what we're keeping track of. If the level is 0, you can get there with 0 steps. If the level is 1, you can get there with 1 step. Because we're visiting everything you can possibly get in k steps, the level is telling you what that shortest path distance is. And the parent pointers are actually giving you the shortest path. That's the cool thing about BFS. Yeah, BFS explores the vertices. Sometimes that's all you care about. But in some sense, what really matters is it finds the shortest way to get from anywhere to anywhere. For a Rubik's Cube, that's nice because you run the shortest path, you run BFS from the start state of a Rubik's Cube, then you say, oh, I'm in this state. And you look up this state, you look at its level, it says, oh, you can get there in 9 steps. That's, I think, the average. So I'm guessing. I don't know how to do this in 9 steps. And then, great, so now you know how to solve it. You just look at the parent pointer. The parent pointer gives you another configuration. You see, oh, what move was that? And then you do that move. I'm not going to solve it. Then you look at the parent pointer of that. You do that move. Look at the parent pointer of that. You do that move. Eventually, you will get to the solved state, and you will do it using the fewest possible moves. So if you can afford to put the whole graph in memory, which you can't for a big Rubik's Cube, but you can for a small one, then this will give you a strategy, the optimal strategy, God's algorithm, if you will, for every configuration. It solves all of them, which is great.